Hi. Okay, so today let's talk about section 2.7. This is where we're going to talk about linear, meaning a line, and absolute value, inequalities. Up till now, we've been talking about linear and absolute values in terms of equality. Okay, that is, they have an equal sign. Okay, so what are our inequality symbols? So, for example, this is the greater than symbol. I can make a small modification to that symbol and put a line underneath it, and that is greater than or equal to. I could reverse it. This would be the less than symbol. And it also could add equality, so we could get less than or equal to. And the last one, which we don't think about a lot, but it is an inequality symbol because it's not equality. This is equality. When I put the bar through it, this means not equal to. So these are the inequality symbols. And we will be using them when we solve inequalities. I want you to look at page 205 of your book. This is a list of sets of numbers and how that gets represented in words, and how we represent an inequality, and in set builder notation. We need to know how to do all three types of these. So be referencing that for the first part of your homework. Because the problem is that when we solve equalities, we'll get one or possibly two answers. When you start solving inequalities, your answers, excuse me, will be an entire set of numbers. So for example, the solution could be x is less than or equal to 7. This is an infinite amount of solutions. Anything less than 7 and including 7 will solve the inequality. So let's just start with some basic sets of numbers. So for example, let's say I want to look at, here's a number line. And I want to look at numbers that are greater than or equal to negative 2. Okay, so negative 2 is our starting point. Okay. And so we put that on the number line. And if we want to look at all of the numbers that are greater than negative 2, remember on a number line, infinity goes this way, and negative infinity, numbers towards negative infinity go that way. So if I'm looking at all numbers greater than 2, it would be all of these sets of numbers. And in this case, I can include negative 2. So this is how we represent it on the number line. If I want to write it in interval notation, okay, interval notation is either going to have parentheses or brackets. Okay. It could also have the combination. We'll see what we mean. Okay. Okay. So these are how they're how interval notation gets capped, either with parentheses or with the brackets. The first number will always be the lowest number in the set, and the second one will always be the highest number in the set. So if we want to represent this in interval notation, the lowest number in our set is negative 2, and the highest number continues on continues on to infinity. Okay. So this is the lowest, this is the highest. Okay. Now the question is, how do we cap these? Now since this is an inequality, that means we can include negative 2. So we put a bracket around it. Okay. Now on the other end, we have to put a parentheses because infinity is a concept. It's not a specific number. So we cannot grab a hold of it. There will always be a number larger than that. So since we can't officially grab a hold of it, we will put on the parentheses. Now there's also set builder notation. Okay. So set builder notation starts and ends with a brace. Okay. This tells you we're looking at a set of numbers. There's a bar in the middle. This will mean such that. Okay. In here we put a generic item. And usually that generic item is, we say, let that be equal to x. Okay. So in the set, here's my generic items, such that, and then I put in a condition. That is, what qualifications must this generic item meet to be in the set? So in our example, it will look like the set of all x such that, and then here is our criteria. Well, it has to be that x must be greater than or equal to negative 2. So these three are all ways to represent this set of numbers. This is the number line, this is the interval notation, and this is the set builder notation. Okay. Here's another example. Let's say now the important number is 7, and that we would like to represent all numbers less than 7, but not including 7. If it's not including, then we will not fill in this circle. The way we could write this in interval notation is, remember this is negative infinity, this is positive infinity. Okay. So the lowest number in this interval is negative infinity. Okay. Now, negative infinity is, again, not a specific number. It's a concept, so it will always get a parenthesis. And then the highest number in the set is set as 7, so I put a comma and then the 7. But now I can't include 7, so I will put in a parenthesis because it's not included. Then its set builder notation would look like this: a brace for the set of all x, such that, well, now what quality has to x have? X has to be less than 7. So these three are ways to represent the same set of numbers. So let's say you wanted to go shopping and that you were looking for, I don't know, a jacket or something like this, and you have some money to spend. You said, I can spend between $100 and $150. Okay. So your range of numbers looks like this. And let's say you have $100, but that you're just short of the 150. So you can spend anything in between there. Then this is how I would represent it on the number line. Now in interval notation, that would go, I would include 100, but we just don't have 150. We're just shy of it. So it would not be included. Then in set builder notation, it would look like the set of all x, such that, well, now x is bounded on both sides. So the way we write that is you take the lower bound, the 100, and the higher bound's 150. X is going to go in the middle of that. So x can be greater than or equal to 100, or x can be less than 150. Okay, so that's how you represent numbers, sets of numbers, 3 different ways. Remember to refer to page 205. There's a lot of other examples in there if you need help. Okay, so we have this let's say, okay, so this is properties of inequalities. So let's say we have sum A that is less than B. Then, if this is true, then what I can do is add the same quantity to both sides, and the inequality still stays true. Now, if C is negative, you could think about it this way. And it would still be true. Okay? So you can add or subtract the same quantity to both sides of the inequality, and it will stay true. Okay? Things become a little bit... Let's just do some examples with that. Okay, so, for example, if we have x minus 15 is less than 4, this inequality is already given to us. I want to undo what's happening x to solve this, and right now it's being 15 is being subtracted. So I could add 15 to both sides. Now this will go to 0, and we'll have x less than, and now 14 plus 15 is 19. So this is the set that solves it. On the number line, then it would look like this, 19. Okay. X needs to be less than that, but not including it, so it doesn't include, so it's an open circle, and then this is less than. Okay. In interval notation, remember this is negative infinity, so the lowest number we can in this set is negative infinity. Then the highest is 19. Okay. 19 is not included, so it gets a parentheses. Infinities are never included. And so this is how you would answer that in interval notation. We can do one more example like that. If we have 6 is greater than or equal to x minus 1, I want to undo what's happening to x, so I can add 1 to both sides. This will go to 0, and then 6 plus 1 is 7. So this reads 7 is greater than or equal to x, which is kind of confusing. I prefer to write it in its equivalent form, where x comes first, okay, So notice which way the inequality symbol is with the x. If I write x on the left-hand side, I need the smaller points to be facing x. And then we can write the 7. So these are equivalent. So saying that 7 is greater than or equal to x is the same thing as saying x must be less than or equal to 7. On the number line, then it would look like this. Here's 7. 7 can be included. And here's the less than portion of it. Its interval would go from negative infinity to 7 with a bracket because 7 is included. Alright, let's now look at multiplication. So multiplication gets a little interesting with inequalities, but once I show you this example, you will see why. So we have a multiplication by a negative. Okay. We know this to be true. We know that the number 3 is less than the number 7. This is a true statement. Okay. Now let's say I want to multiply by a negative 4. Okay. If I do it on one side, I need to do it on the other. And now what our statement reads is that, let's see, negative 4 and 3 is negative 12. 7 and negative 4 is negative 28. Okay. And we would just bring this down. However, this is not true anymore. Okay. On a number line, remember here's 0. I'll go some negative amount, negative 12. And then I go further to get to negative 28. So negative 12 is in fact greater than negative 28. So what we actually have to do is when multiplying or dividing by a negative, we must flip the inequality symbol for this exact reason. Okay. So let's look. What do I mean by that? Let's look at this example. So for example, we have negative 2x minus 1 is greater than or equal to 5, let's say. Alright. I want to undo what's happening to x, so I'll add 1 to both sides. So this is minus 2x. It's now greater than or equal to 6. And now negative 2 is being multiplied to the x, so I want to divide by negative 2. Okay. These will cancel. So x, now negative 2 goes into 6, negative 3 times. But I can't just copy this inequality symbol, I need to flip it. So this would be the solution for this equation. Let's try another example. We have 4 minus 3x. Let's divide that entire thing by 5 and say that that's greater than or equal to 3. So if we needed to solve, again, we want to undo what's happening to x. And here's a fraction, and I don't like that fraction. It's easier to get rid of fractions, though, so I could just multiply both sides by 5. Okay. And then these would cancel. So that 4 minus 3x is greater than 15. Now continuing to undo what's happening to x, I could subtract 4. So negative 3x's must be greater than 11. And now dividing by negative 3, the negative 3's will cancel. So we have that x, now I want to write this, let's move the negative up top. Okay. But if I'm going to do that, I have to remember to flip the inequality symbol. So one thing we could do is, let's start from here. 4 minus 3x is greater than 15. Let's say I notice that there's this negative here. I could have done this in an alternative way. I could have added 3x to both sides. So now this would go to 0, and we'd have 4 is greater than 15 plus 3x. By doing that, I've made the coefficient on x positive. Okay. Now we'll subtract the 15. This will go to 0. This has to be greater than 3x's. And 4 minus 15 is negative 11. Now I can divide by 3. So that x, and then on this side I have negative 11 thirds. But notice that these are saying the same thing. Okay. Here we have x is less than, the arrow is pointing towards the x, negative 11 thirds. Here we're saying negative 11 thirds is greater than x. But notice that the arrow is still pointing to the x. So these are equivalent statements. I always like to write it, even if I come up with something like this, I like the x to be first, so I just have to make sure I keep the tail pointing towards the x. Okay, let's do some more with fractions, so we get comfortable with those. Negative 3/4 x is greater than or equal to negative 5/8 plus 2/3 x. There's a couple ways we could go about this. Since I have x's on both sides of the equation, what I could do is that I could add that to the x's to both sides. However, that would require adding and subtracting fractions. So I think possibly if we got a common denominator and then multiplied through by that common denominator, we could get rid of the fractions. So our least common denominator here, 4 goes into 8, but 3 doesn't. 12 is not big enough because 8 doesn't go into 12. I could double this. 16. 3 doesn't go into 16. So let's see. Let's look at these factors. Here's 2 times 2 times 2. And this is 2 and 2. Okay, so I'm going to have 2's here and a 3 from here. And the most amount of times the 3 is represented is only once. So we'll put that to the first power. And the most amount of times a 2 is represented is 3 times. Okay. So our least common denominator is going to be 8 times 3, which is 24. Alright, so to do that, okay, here, I have 2 of the 2's, so I need to multiply by the 2 and the 3, which is 6. Right. Here I have 3 of the 2's, so I just need to multiply by a 3. And here I have the 3, but I don't have the 2 cubed, which is 8. So that's a way to think about getting a least common denominator. So now let's write that. Okay, so this side will be over 24. And let's write this side as over 24 as well. Okay. The greater than or equal sign will stay. Now 6 times negative 3 is negative 18. And we'll put the x. Okay. And then here, negative 5 and positive 3 is negative 15. Plus, and now 2 times 8 is 16. X. I could also write this x up top if we would like. Doesn't matter. It's saying the same thing. Okay. Now we can multiply through. Now that we have the same common denominator, let's multiply both sides by 24. And then they will cancel, leaving just the negative 18x is greater than or equal to negative 15 plus 16x. So in one step, we've gotten rid of all of those fractions that are such a pain to deal with. And now we can just solve this. We could, well, we could get to 16. So let's subtract 16x. So this will be greater than or equal to negative 15. And now here, what we have is on the number line, here's 0, I've come down to negative 18, and then I'm going an additional negative 16 units. Okay. So 18 plus an additional 16 units, 12, 14, carry the 1 is 34. In total, I'm negative 34 units. So negative 34x must be greater than or equal to negative 15. I'm going to divide by the negative 34. And then this will cancel. So we'll have x. Now on this side, we have 15 over 34, which is positive, because a negative and negative become positive. But I've divided through by a negative, so I need to flip this inequality. And so this is our solution set. Okay, let's try one more. Negative 5/6 of x less than 3/4 plus 8/3 x. Now again, I could add this over, but then I'd be adding and subtracting fractions. So let's just get our least common denominator. This is 3, this is 2 and 2, this is 2 times 3. So all of my factors are again 2 times 3, and then I have to decide what power. So here's a 3 to the first power, and here's a 3 to the first power, so our least common denominator only needs a 3 to the first power. For the 2's, here's a 2 to the first power, here's 2 to the second power, so the most amount of times we see 2 is squared. Which means our least common denominator, 2 squared is 4 times 3, which is 12. Okay. So to get to 12, I'll multiply this by the other 2. We'll multiply this by 3. We'll multiply this by 4. And so now our our least common denominator is 12. In between, we'll keep the less than or equal to sign. This becomes negative 10x. This is 9. And 8 and 4 is positive 32x. Now that we have the least common denominator, we can clear these fractions. So let's multiply by 12 over 1 on both sides. That will cancel. And we'll be left with negative 10x less than or equal to 9 plus 32x. And now we can solve this. This is just a simple linear equation. Let's subtract 32x from both sides. So on the right-hand side, we'll have less than or equal to 9. And again, we're in this situation of becoming more negative. If here's 0, then I go down negative 10 units, and then I'm going down an additional negative 32 to get to negative 42. Now we can divide by the negative 42. 42's will cancel. And on this side, again, I like to move that negative up top so we don't... I like to move the negative up top, so it's negative 9 divided by positive 42, just because it's easy to forget about this and lose it when it's in the denominator. But in this case, remember, I've divided by a negative, so I need to change this. And I suppose we should put this on the number line just to remind ourselves. Okay, so negative 9 over 42 is our important value. We need x can be equal to it, or it's going to be greater than. So it would look like so. Remembering over here is positive infinity. And we could also represent this in interval notation. Now in this case, the lowest number that x can be is negative 9 over 42, and the highest value it can be is infinity. Infinity is a concept, not an exact number, so it will never get a bracket. But negative 9/2 can, because it's included. We can also talk about compound inequalities. So what that means is we have multiple inequality symbols. So for example, if we had 3 less than or equal to 2x plus 2, and that would be less than 6. So this is actually a compound inequality. I just have 2 symbols to deal with. Okay. But we can solve across all 3. So I want to undo what's happening to x, so I'm going to subtract 2, but I have to do it from all 3 sides. Okay. So in between, we have 2 x's, keeping the symbols the same. 3 minus 2 is 1, and 6 minus 2 is 4. Now I would like to get to x, so I need to divide by 2. So in the middle, the 2's cancel. We have just x, and on this side, 4 divided by 2 is 2. On this side, 1 divided by 2 is just a half. So here's the solution for that. And we could look at a number line. Now we have two boundaries, 1/2 and 2. And x is going between those. In this case, the 1/2 can be included, so I would fill that circle in. But for the 2, it will not, so I'll leave that symbol open. And now the inequality looks like this. The lowest number we can take on is 1/2. The highest value we can take on is 2. 1/2 can be included, so it'll get a bracket. 2 cannot, so it will get a parenthesis. Let's try another. 3y is less than 4 minus 5y, which is less than 5 plus 3y. Okay. Now in this case we have variables on all 3 spaces. Okay. We want that the variable will be in the middle. So I'm going to try and move all of these over. So if I subtract 3y, I can subtract 3y, and I can subtract 3y. We're lucky that these are the same 3y values. They will help us. Sorry, I need to focus this a bit better. Okay. So now what we have on this side then is that we have 0 is less than 4, now minus 8y, and that's less than 5. These will go to 0. Okay. We need to undo what's happening to y, so we'll subtract 4 from both sides, all sides. Okay. So in this case we have negative 4 is less than negative 8y, which is less than 1. Now I just have to undo what's happening to y. So let's divide by everything by negative 8. So now the negative 8's will cancel. We're left with y in the middle. On this side, well, 1 divided by negative 8, that's just negative 1/8. Here, a negative and a negative become positive, and 4 over 8 is 1/2. But I have to remember that I divided by a negative, and so I need to flip these symbols. I don't like writing it this way. Notice that it doesn't follow in how the number line goes. I would really like to have it as it goes on the number line. Negative 1/8 is less than 1/2. Okay. So now, if I was to write it this way, so this is what I mean on the number line. Okay. Negative 1/8 is less than 1/2. Okay. And so I like writing it this way so I can figure out how to fill in the number line. Okay. In this case, if we're just looking at the 1/2 and the y, the arrow is pointing toward the y. So I need that to be true here as well. I need the arrow to point towards the y. On this half, the arrow is pointed towards the negative 1/8. And if I'm going to rewrite it this way, I need to make sure that the arrow stays pointed at negative 1/8. And so then I can answer these next questions very easily. If I need to draw this on a number line, negative 1/8 and 1/2 are not included, but anything in between is. And if we had to write it in interval notation, we'd get negative 1/8 up to 1/2, and neither of them are included. Okay, so let's try one more. Let's say we had to solve 5 minus x is less than 4 and 0.2x minus 5 is less than or equal to 1. Okay, so we're going to have to satisfy both of these things. Okay, well, we can do that. Let's just solve for x. Okay, so I'll subtract 5 from both sides. So negative x is less than negative 1. And then we'll divide or multiply, however you want to think about it. Let's multiply this by a negative 1. So we have that now positive x and positive 1. But if I'm going to do that, we need to flip the inequality symbol. Okay. So that's one solution. Okay. Now let's solve here. We're going to add 5 to both sides. So 0.2x is equal to 6. Did I do that right? Yeah, plus 5. Okay. Now, I don't want to go dividing by a decimal. It's not necessarily how I'd like to do that. So that's okay. Let's just multiply each side by 10 to get rid of that decimal. So on this side, multiplying by 10 is the same as moving your decimal point one place. So we get 2x is equal to 60. And now we can divide by 2. So that x is equal to 30. Oh, shoot, you guys. These are not equalities. They're less than or equal to. Sorry about that. So x is less than or equal to 30. Okay. All right. So these are our two situations. X needs to be greater than 1, and x needs to be less than 30. Okay. So let's try and represent this on the number line, because we have to satisfy both of them. Okay. From here, x must be greater than 1. So here's 1. Okay. X cannot equal that, and then be greater than. Okay. Now from here, let's say here's 30. Okay. X needs to be less than this. Okay. And it can include 30. So the question becomes, what is it? What is our answer? I have to satisfy both of these. So what I have to do is I have to find out where these overlap. That is called the intersection of the two sets. So the intersection is where they overlap, and so any number in between 1 and 3 agree in both sets. And in fact, 30 agrees in both sets as well. So we can include that one. However, 1 is in this set, but not in that set. So it can't be in the intersection. It doesn't overlap. So this represents what our actual solution is. And now let's just write it in interval notation. So the first one is 1, but it's not included. And the highest number we can take is 30, and it is included. If I wanted to write this in inequality or set builder, it'd be the set of all x such that the lowest bound is 1. X will go in between that and 30. I'll close the brace for the set builder notation. X can be greater, but not including 1, and less than or equal to 30. So sometimes you might actually have to draw them out and figure out what the solution set is.